Alright, in this set of videos we're going to talk about refraction. And what I have here is a laser pointer. Move the camera just a little bit so you can see better. Laser pointer. This is just a plastic block. This is a specific type of plastic called acrylic or lucite. And then just a box in front of here so you can see how the light is falling. But what I'm going to do is shine the laser through here. And I want you to notice, it may be kind of hard to tell, but I'll rock the laser up and down for a moment just so you can see what you need to see. Hopefully you can see this, but at this beginning point I want you to see right here that the light is actually bending as it moves into the piece of lucite. Let me get a green laser, perhaps it's a little bit easier to see. Here's the green laser, much better. Ooh, that works even better. So there you can see, now you're actually noticing on this side over here, you'll see that there's some light reflecting off. That's not what I want us to notice here. But we see the light coming in. It bends to the left as it goes into the block of lucite. And then as it comes out, it bends again to the right. Okay? And I'll put the red one back on there so I can do something else with that. Notice with the red one, we could see the beam. So there's our beam. I want you to notice what happens right here on the point of light that's directed on the box. Notice what happens to that point of light as I pick the block up and down. The point of light is just moving over. Moves to one side and then to the other. And you can almost see, yeah, there's where the light is going straight through, and then you can see almost simultaneously the path of light that it actually takes through the block. So the point of all this is that you can see that the light is bending. That's due to refraction. And we're going to talk about refraction in this video. This light is not staying in the same medium. The light is going from the air into the lucite and back into air. When we change the medium of any kind of wave, including light, if you change the medium, you change the speed, and with light, when you change the speed, you change the direction. So let's talk about refraction. Alright, first, to start on the notes, we know the speed of light is 3 times 10 to the 8th meters per second. We're going to use the letter C for that. This is C as in E equals mc squared, and C as in another equation that we're going to talk about today. But realize that this is only the speed of light in a vacuum. Whenever it moves through any other substance, it actually slows down. When it travels through a more optically dense medium, it slows down. And as light changes speed, it also changes paths. And we'll talk about the reason for that in just a moment. Alright, so the first part, this top part of the notes is really important, where it says slow down light and speed up light, because you have to know exactly what light does in these two specific circumstances. First of all, when light moves from a less optically dense medium to a more optically dense medium, for instance from air into water, so this is the picture that I want you to draw in that space, light coming from air into water, it slows down, right? And the reason why it slows down, I want to draw for you right now. So let's imagine, and I used this analogy before, but I want to use it again just to make sure we're on the same page. This is the side of a road. This roadway is made of concrete, and let's say we have sand over here on the side. If you're driving late at night, you might get tired and you're going to run your car off the road, something like this. And the interesting thing about when you do this is because if you look at this point in time, the pathway or the locations of your tires may look something like this. Okay, that's where your tires actually are. And it's interesting because your front right tire is the first one to contact the new medium. When that happens, this tire is going to slow down because it's harder to move through sand. This is the same as when you're in the grocery store and you hit something on the floor, or a piece of gum or something like that. It usually will bind up that wheel and it will cause your grocery cart to pull to one side. And the same thing happens here. So we've got your car going this way, this one's going to slow down while this one continues to move at the same speed. And so instead of your car traveling in a straight line the way it was before, what's going to happen is it's going to turn a little bit. It's going to move off in this direction. And there's a line right here that we can look at that is perpendicular to the boundary between these two quote-unquote media, and that line will be called the normal line. This is what happens with a car, and the same thing happens with a wave. The point with a car and a wave is that both are three-dimensional objects. They take up space, and because they take up space, part of the wave, just as part of your car does, part of the wave enters the new medium before the rest of the wave does, and for that reason we get this bending effect. So that's the reason why the light will bend toward the normal. And that's what all this text is talking about here. If there's a truck on a smooth road and it suddenly hits a patch of sand at an angle, the first tire to hit will slow down and the truck turns toward the normal. This make sure that you write somewhere close to where you're drawing this and circle it. You need to know that when light slows down, it bends toward the normal. You need to write that somewhere on your notes. When light slows down, it bends toward the. The second scenario is when light speeds up, and what we're going to do is we've simply switched these two media. Instead of going from air into water, now the light is moving from a more optically dense medium into a less optically dense medium, such as from water into air. In that case, it speeds up. It gains speed because we have a lower index of refraction here. And again, the reasoning, we're going to use the example of the car or a truck driving on a road, except now instead of going from the smooth road into the sand, we're going to go from the sand onto the smooth road. So let's look at that. So here was your car before, and let's say now you wake up and you're going to head back onto the road this way, and the same thing happens here. Your car does not contact the new medium all at the same time. So as this happens, in this case, the driver's side, the front left tire is the first one to hit, and in this new medium it's easier to travel, therefore this tire would be moving faster while these other three are going slow. And the effect that will have is, instead of moving off in a straight line, your car always turns toward the slower wheels, and so the car will turn in that direction. Once again, we have a line here that's perpendicular to the surface called the normal, and your car has now turned away from that normal line. So that's what you need to write somewhere close to where you're drawing that other picture that you have on there, and I'll put that picture back up in just a minute. Don't draw this one on your notes. This is just for example. But somewhere close to where you need to draw the other picture, write this, that when light speeds up, it bends away from the normal. NORM. When light speeds up, it bends away from the normal. So this is the picture that I want you to draw right here of the light coming in from water back into air. Here's our normal line, and it will bend away from the normal. A couple of things that we got to notice about this. These two symbols that you see here, even though they're small, this is theta I, this is theta R. We've seen those before. Before, they represented the angle of incidence and the angle of reflection. And with reflection, the mathematical relationship between those two was that they were equal. All right. We can see here, I'll redraw the picture that we were looking at earlier. We can see here that these two angles are no longer equal to each other because we have a bending. This one doesn't go in a straight line. It bends either toward or away from the normal, and so this is no longer true with refraction, and this one is no longer the angle of reflection. This is the angle of refraction today. So they are not equal to each other because the light is bending. If it didn't bend, if the light just went straight on through, these two angles would be equal to each other because you would have vertical angles here, but that's not the case. That's not what we have. Because the light bends, those two angles can no longer be equal to each other. So we'll talk about the specific mathematical relationship between those on the back of the notes. But for now, the most important thing you got to know is that when light speeds up, it bends away from the normal. And when it slows down, it bends toward the normal. Extremely important to know for this top part. Now, it's also important to know that with each different material, the light doesn't bend the same amount. Each different material refracts light slightly a different amount, and how much light is refracted is dependent on the index of refraction. And the index of refraction is simply the ratio of the speed of light in a vacuum, which is always c, 3 times 10 to the 8th meters per second, to the speed of light in any other transparent substance. Anything, whether you're talking about water or glass or plastic or Sprite or whatever else, any transparent substance is going to transmit light slower than the speed of light in a vacuum. The larger the index of refraction, the slower light will travel in that substance. And we also need to memorize that for air, the index of refraction is 1. At least we consider it to be 1 in this class. It's actually like 1.00003, but we consider the index of refraction for this class to be 1. This is because of this equation, N equals C over V. This is equation number 48 in your chart. N, the index of refraction, is equal to C, the speed of light in a vacuum, which is always 3 times 10 to the 8th meters per second. So you'll never have to solve for C. It's always 3e8. And V is the velocity of light in whatever other transparent substance we're talking about. Again, glass, plastic, maple syrup, blood, whatever it is that you're sending light through. We can calculate the index of refraction for that material by doing 3 times 10 to the 8th divided by the speed of light in that substance. So let's look at a practice problem for this one. The hardest mineral is a diamond with an index of refraction of 2.42. At what speed does light travel through a diamond? You need to know that index of refraction is N. That's 2.42 that they're giving us. At what speed does light travel through a diamond? That's V that they're asking for. They're not asking for C because we already know it. So N is 2.42, C is 3 times 10 to the 8th. We want to know V. We plug the numbers into this equation, and algebraically to solve this, to get the speed of light, you would end up doing 3 times 10 to the 8th divided by 2.42. For a number of different reasons, you could multiply by V on both sides, which moves V over here, and then you would divide by 2.42. In either case, you get 1.24 times 10 to the 8th meters per second. So this is the speed of light in a diamond. And that happens to be, as far as percentages, it happens to be about 41% of the speed of light in a vacuum. All right, so that's how we use that equation, N equals C over V. In the next set of notes, we're going to move to the next video. We're going to move to the back side of the notes and talk about Snell's law.